Dear friends, today we will see example number 8.4, that is illustration on page number 193 of chapter number 8. Now, what is the information that is provided? We are given that two uniform solid spheres of equal radii r, that is capital R, but mass capital M and 4m have a center to center separation of 6 capital R as shown in the figure. Now the two spheres are held fixed. A projectile of mass small m is projected from the surface of the sphere of mass capital M directly towards the center of the second sphere. Now obtain an expression for the minimum speed v of the projectile so that it reaches the surface of the second sphere. So as shown in the figure, we are having two spheres of same radii, but left side sphere has mass capital M while right side sphere has mass 4 capital M. Now we project a small object, that is small m, with velocity v, and the separation from center to center that is given, that is total 6r. Now the neutral point n that we have shown with red color is defined as the position where the two forces cancels each other exactly. That is, if we say that On is equals to R, we can have the equation of force, that is gravitational force at point N due to left sphere, that can be given as G m small m over r square. But as we know that at that point the object get neutral force, that means the force due to right side sphere, that is of mass 4m on point N, is also given by, that is G 4m small m over 6r minus r whole square. Now we can compare and cancel out the equal terms. So here the equal terms, that is capital M, capital N, capital G and small m, that all are cancel out. Now what remains here? So it is clear that the remaining term, that is 1 over r square, is equals to 4 over 6r minus r whole square. Now from this, if we compare the equations, we can have the equation, that is 6r minus r whole square is equals to 4r square. So now when we simplify it, we have, that is 6r minus r whole square, that is equals to 2r whole square, and therefore 6r minus r is equals to 2r, that is plus or minus 2r. So here we can have that 6 into r is equals to either 3r or 6r is equals to minus r. Therefore, if we say that small r is to be defined, then r is equals to 2 times capital R, or r is equals to minus 6 capital R. Now it is very clear that the neutral point r is equals to minus 6r does not concern us in this example. Thus, ON is equals to small r is equals to 2 capital R is accepted. Now it is sufficient to project the particle with a speed which would enable it to reach up to capital N. Thereafter, the greater gravitational pull of 4m would suffice, and the mechanical energy at that point capital M is. So now we know that mechanical energy remains constant, and suppose at point M or at sphere M, the mechanical energy at M, what it is given, that is EI. Now EI is equals to first 1 half mv square, that is kinetic energy, that is 1 half mv square. Then potential energy due to capital M and small m system, so that will be minus G capital M small m over R, and potential energy due to capital 4M sphere, that is minus 4 G M M over 5 R. Sorry, it will be capital R. So 5 capital R. In the same manner, at point N, that is the neutral point, the speed approaches 0 because both the force will be equal, and the mechanical energy at N is purely the potential energy. So now at point N, we can say that at point N, the mechanical energy becomes purely potential. So energy at point N is given by, now the distance of small r is obtained as a 2r in above example, in above calculation. So the potential energy at point N, here we have to see this in the figure, that the potential energy at point N, that is at red point, is equals to, that is GMM over small r, that is 2r, and from that, here if this small r is 2r, then we can say that this distance would be 4r, as total distance is 6r. If this is 2r as per as the calculation, we can say that this will be 4r. So now we will apply this condition in our example. So the potential energy at point N, we can have the equation that is minus g m small m over 2r. Then for the 4m mass, minus 4g capital M small m over 4 capital R. So now here we have two different equation for the potential energy. Suppose we say this as equation 1 and this as equation 2. Now we can compare this as a mechanical energy equation. So from the principle of conservation of mechanical energy, we can compare them and we can get the equation like from 1 and 2. We can say that from equation 1 and equation 2, what we obtain that when we compare EI is equals to En as per as the conservation of energy. Now what it will remain, so what it will provide us, that is 1/2 mv square minus g capital M small m upon small r, that is now 2r, minus 4g capital M small m upon 5r is equals to, so now let me say this r is now 2r as we have already obtained it, is equals to minus gmm over 2r minus 4gmm over 4r. Here I have to change the equations, that is minus 4g m small m over 4r. So here now when we compare, we can have the equation of comparison and we obtain the equation as, when we compare it, we have cancel the small m from all the equations and ultimately we have the comparison part as one half v square minus g m over r, that is actually small r that should be there. So here the equation consists, that is capital R in the above equation, so there should be capital R in this equation 1. We have put a small r, but in place of that it should be a capital R. So here also in the question it would be R only, so we can replace it with R only. So here this is minus gm over r minus 4gm over 5r is equals to minus gm over 2r and minus 4gm over 4r. So here also we can cancel out the 4 term and we can obtain the term that is r. Now this gm over r term cancel out in both the side. So here this gm upon r and this gm upon r will cancel out. So the remaining part that will be, now we can say that is v square upon 2 is equals to, this term will move to the right side. So the equation will be 4gm over 5r minus gm over 2r. Now we can take common what we can have. So if we take common the remaining part as capital G capital M over R, that will remain 4 by 5 minus 1 by 2. So this is the remaining part and that is the answer. Now if this is v square by 2, so if we make v square as a subject, then we have v square that is equals to 2gm over r. Then we can take the LCM over here. So it can be 4 2s are 8 minus 5 that is 3 upon 10. If we take the ratio 5 are 10, that is gm over r 3 by 5. So this is your v square. Now if we take the square root of t, we can have the equation that is the v is equals to square root of 3 by 5 g capital M over r. So this would be the equation of velocity. A point to note is that the speed of the projectile is 0 at n, but is non-zero when it strikes the heavier sphere 4m. The calculation of this speed is left as an exercise for you. So you can calculate it and we can have the value if we consider it in the term. 5 of the chapter 8. Now that is also an interesting example, but some part of that example are to be considered out of the course, but still we can remember the equations and we can calculate this example. So first of all, we are given information that we will read. We are provided that the planet Mars has two moons, that is Phobos and Deimos. First, Phobos has a period of 7 hours 39 minutes. So periodic time of first planet, that is first moon, that is Phobos, has given that is 7 hours and 39 minutes. So overall, if we go, it is given, that is, when we convert it into second, we can have the equation. Another thing, that orbital radius is about 9.4 into 10 to the power 3 kilometer. So orbital radius is also given for Phobos, that is 9.4 into 10 to the power 3 kilometers. So that is radius is also given. Now here first of all we will convert the hour and minute into seconds. So first of all we will convert these hours into minute. So it is very clear that T1 over here having 7 hours, that is 7 into 60 minutes plus 39 minutes. So first of all we have converted it into minutes. So it is clear, 7 6 are 42, so it is 420 plus 39 minutes. So total minutes are 459 minutes. Now if we want to convert it into second, we can say that this is 459 into 60 seconds. So we have converted the periodic time into second. Now R1, that is distance given in a kilometer, that can be converted into meter, that is 9.4 into 10 raised to 6 meter, because 1 kilometer is 10 to the power 3 meter. So that is also given. Now we are asked calculate the mass of Mars. So we have to calculate the mass. So suppose mass of Mars is given as mm, that we are asked to find out. We can say that is T1 square is equals to, from the earlier equation of the periodic time, we can have 4 pi square, so that is 4 pi square over g into m. Here m will be the mass of Mars into r1 cube. So r1 is the given value. Now we have to find out m of m. So we will make the subject as a mass. So we can say that therefore mass of Mars is equals to 4 pi square into r1 cube over g into t1 square. So now when we simplify this, we can get 4 into 3.14 whole square, now into r1, that is 9.4 whole cube into 10 to the power 18, then g, that is 6.67 into 10 to the power minus 11, and t1, that is 459 into 60 and its whole square. So now this term is, when simplified, we get the mass of Mars, that is comes to be 6.48 into 10 to the power 23 kilogram. So that is the observation, that mass of Mars we can obtain. We are also asked another question in the same question that they have asked us, assume that Earth and Mars move in circular orbits around the Sun, with the Martian orbit being 1.52 times the orbital radius of the Earth. Now, what is the length of the Martian year in days? So now again Kepler's this equation that we have applied, we can put it here. The same equation that we can say that Martian days period, that is Tm square over T Earth days, that is also the periodic time square, is proportional to RMS cube over RES cube. Here MS is a RMS is a Mars and Sun distance, and RES is Earth and Sun distance. Here obviously we can say that Tm square, here RMS and RES are almost same taken, but the value of the term that RMS is about 1.52 times. So here it is clear that we can say that Tm square over Te square is equals to 1.52 times the value. Now having the cube term that we left over here, so now when we take Tm as an equation, we can have 1.52, that is 3 by 2 into Te. So now this will be the equation, and when we put the values regarding Earth, so the periodic time of Earth is about 365 days, about the Sun, so here it will be 1.52 raised to 3 by 2 into 365 days as far as Earth concerned, and therefore this answer almost would be equals to 684 days. So the question that they have asked as the answer is 684 days. Now another example, that is example number 7, that we will concern now. In this example number 7, it is given that express the constant k of equation number, that is T square is equals to k Re plus h cube. So we have the equation that is T square is equals to k Re plus h cube, and we have to express the equation of k that in days and kilometers with the given value of k, that is provided 10 to the power minus 13 per second square per meter cube. So here the moon is at a distance of 3.84 into 10 to the power 5 kilometer from the earth, and obtain its time period of the revolution in days. So here what we will do, we will apply the equation simplification, that we are given k. First of all we will convert it into SI system to days and kilometer. So first we want to convert it, we can have 1 over 24 hour for one day and 360 square. So this would be our term in a day square. Then another we have that is 1 over 1 by 1000 meter, that is converted into kilometer, that is kilometer cube. So if we simplify, we have the simplest equation, that is 1.33 into 10 to the power minus 14 days square per kilometer cube. So this would be the equation for K. Now just put it in the equation that we are given for the periodic time, that we can have T square is equals to K into R cube. So here we can say this is 1.33 into 10 raised to minus 14, and R, that is 3.84 into 10 raised to 5 and whole cube. So this would be about 27.3 days. So here the T will be about 27.3 days. Here this equation is only also holds for elliptical orbit if we replace Re plus H by a semi-major axis of the ellipse. The Earth will then be at one of the foci of this ellipse. Hello dear friends, now we will see an example number 8.8, that is illustration on page number 196. We are given that a 400 kilogram satellite is in the circular orbit of radius 2 Re about the Earth. So mass is given, that is about 400 kilogram. So this mass is of satellite itself. Now it is about 2 Re from the Earth. How much energy is required to transfer it to a circular orbit of radius 4 Re? What are the changes in kinetic and potential energies are also asked. Now we know that we have the equation, that is total energy E, that can be represented as minus G MEM over 2R dash, where R dash is the given distance. Here in first case R1 is given as a 2 Re, and in second case we have to send it to the 4 Re. So for case 1 we can say that case 1 we are provided EI, that is minus G MEM over 2 into 2 RE, and therefore this equation would be, that is the term EI, that would be minus G MEM over 4RE. So this is your initial energy, that is total mechanical energy. Now we have to send it to the distance, that is 4 Re. So in the final condition, that is case 2, we have to send it to the distance 4 Re. So energy finally, that we can say that minus G MEM over 2 times 4 Re, and therefore this equation would be, that is minus G ME m over 8 RE. So this is final mechanical energy. This is final energy. Now we have to find out the change in total energy. So now change in total energy, we can say change in total energy, that is delta E is equals to EF minus EI. Now the term that we can obtain over here is minus GMEM over 8RE, and this minus minus will be plus, that is GMEM upon 4RE. Now when we simplify it, we get that is GMEM over 4RE. This will be in a suffix. So that would be in the suffix RE. Now this is the equation in which we convert it into the gravitational acceleration form. So we multiply and divide with RE. So this will be GME over RE square. So it would be M into RE over 4. So this will be 1 by 4 GM RE. Now when we put all the values that can be obtained with the equation, here we get answer as 8, not the 4, but it would be 8. Now we get the answer 1 by 8 into 9.8, then mass is given 400 kilogram, and the radius of earth that can be taken as 6.37 into 10 to the power 6. Now when we simplify it, we get the energy, that is 3.13 into 10 raised to 9 joules. So that would be the total change in the energy. Now we are also asked to find out the change in total kinetic energy as well as in the potential energy. Now we know that the change in total kinetic energy is just the mimic of delta E. So change in delta K is, that is Kf minus Ki. That would be exactly the same but with minus sign of the total energy that we have obtained, that is minus 3.13 into 10 raised to 9 joule. And we also know that delta V is 2 times delta K. So that is minus 6.26 into 10 to the power 9 joules. So this would be the change in potential energy that we can obtain.